So one of the questions that will be evaluated at the end of an epidemic is its size, to say how big was this epidemic, like COVID-19, like how big was it? And when we talk about the size of an epidemic, we are simply referring to like the total number of individuals who have been infected by the disease and by the end of the outbreak. So in this context of SIR that we are looking at, then the final size of the epidemic depends on several factors, and that also includes the model parameters and the initial conditions. We need to take note now to say, so these guys, they are actually important at every step. And Howard actually tackled this situation by looking for the limiting number of susceptible individuals. And he said, okay, let's look, for example, and say, look, R naught is equals to, like R0, like the initial number of recovered is equals to 0, all right? That's what we want to assume and say, look, what happens when the initial number of recovered is equals to 0? So then that modifies our equation 6. If you still remember equation 6, it was stating that ST, that was the solution that we actually got in the previous video. So it was saying ST is equals to S0 exponential of minus B over V, RT minus R0. So now it becomes an issue that R0 is not there. Now we are only left with RT. Now, if we do that, then we can divide, because we are looking at what happens is time goes to infinity. What happens to the number of susceptibles? And what fraction of the total population remains and as t goes to infinity. So we are looking at the limit of the number of susceptibles as t goes to infinity. And we get this result that we've got here. And remembering, of course, that we were saying that as time goes to infinity, the number of infected becomes completely 0, because we want the disease to go away, isn't it? So that is the situation that we need to bear in mind, and at the end of the day, we get equation 7 that we have got here. And if it happens that initially the entire population is susceptible, then we have got the simple transcendental form of an equation, and it is made up of a logarithm, and then that will help us actually to plot what happens between as R naught is being varied for particular values within a certain range. So we can actually vary the values of R naught and say, if R naught is this much, then what happens to this transcendental function that we've got? And if R naught is that one, but then what that gives us, it gives us the effect or the effectiveness of, number one, R naught itself, because in this case we're going to make R naught the subject of the formula. And number two, we realize that at the end of the day, as we keep on increasing our R naught, as R naught keeps on pushing down, increasing, from the results that we got, we realize that it's a numerical solution that we are giving. So we realize that the attack rate, the total fraction in which individuals get infected also becomes more and more, because S infinity over n, 1 minus S infinity over n is the attack rate. All right. But then you realize also that we are pushing these models too far, because, I mean, if we push this SIR model too far, we are also going to take note of the fact that, look, we get unreasonable results. And we are going to demonstrate that in Python, that if we assume that our R naught is maybe 1,000, because it means that the one person is actually affecting, is spreading the disease to, is giving the disease to, passing the disease to 1,000 people at the same time. And that's ridiculous, all right? So that's what we want to show in Python, the plot, and just for us to have a feel, just for us to have a feel of what happens within an epidemic. How far is an epidemic prepared to go, and at what point does, in any case, just start vanishing away? All right.